We'll go ahead and get started, and I'm excited to introduce our speaker today, though perhaps I should have had Dr. Lamont do this as he speaks French and is from France. But Dr. Julian Kavanaugh is an assistant professor of neurology at Emory University, where he serves as Associate Division Director of Hospital Neurology. A native of the Loire Valley of France, he earned his medical degree from the University of Paris. He completed a residency in psychiatry at Jules Verne University in France before moving to the United States for neurology residency at the State University of New York. He then pursued fellowship training in advanced general and autoimmune neurology at Harvard Medical School. Dr. Kavanaugh's clinical work focuses on inpatient and acute neurology with a special interest in neuroimmunology and systems-based hospital care. He recently completed the Harvard Medical School certification in artificial intelligence and healthcare, and his grand rounds on AI in neurology with Emory has inspired new collaborations in health informatics and applied machine learning. In addition to his academic work, Dr. Kavanaugh is also a medical correspondent for the Canadian Broadcasting Corporation, where he provides expert commentary on neuroscience, technology, and medical innovation. Thank you, Dr. Kavanaugh. Please.
And thank you so much for this invitation. So this is my only disclosure, Radio Canada, which you mentioned. And as you mentioned as well, I'm a native of the Loire Valley. This is my favorite castle, Chaumont-sur-Loire. And when you grow up in the Loire Valley, there's a character that keeps coming back over and over, and that's Leonardo da Vinci, or Léonard de Vinci as we call it there, because he was brought by King Francis I to his invitation, and this is where he's buried in Amboise, where my grandmother was born. And Leonardo da Vinci brought us a fairly mechanistic vision of the human body and the human brain. And if you think about it, for as far as we can remember, when we explain to our patients or to the world how the brain works, we easily use technological analogies, clocks, automatons, telegraph, computer, etc. But with artificial intelligence, things seems to change, the change of paradigm. And we seem to now be using biological analogies to explain how AI works, to explain the mysteries of AI. And so when I did this certification in AI, I thought that us neurologists and neuroscientists will be particularly positioned to understand how AI works. So that's the foundation of this talk, which will take you through the history and foundation of AI, how some of the core models work. So you have some critical thinking about the data, explaining how some of these AI models work, what applications of in neurology we can use. There are some examples that we'll pepper the talk with as we go along and try to dive into the future of consciousness, robotics, and other future ventures. So the history of AI starts before the term is even coined, and which is 1956, with cybernetics, which is basically a bunch of feedback loops with an animal-machine interaction. Think about how the feedback loops of a cerebellum and insulin pump works. And that's one of the first idea of autonomous machines. An automated theory, which is a machine that is autonomous, but has various components that needs to go through different cycle and transition from state to state, a little bit like a sleep cycle. Those are the prototypes of the autonomous machines before the term artificial intelligence is coined. But it's during the 1956 Dartmouth workshop that the term artificial intelligence is coined. And this is a group of some of the most brilliant mathematicians and computer scientists of the time and tried to imagine their spirits. It's 10 years after the end of World War II. They have witnessed physicists figuring out the atom and the Manhattan Project. And they think they're going to gather over the summer and figure out this artificial intelligence thing and make it possible. Obviously, that did not happen then, but they came up with some key concepts that are absolutely relevant to the way we envision artificial intelligence today. The first concept is this has to be an automatic computer that simulates intelligence, but does not just crunch computers like a super calculator, like a glorified calculator. It has to be a language processing machine that is able to understand language, but also produce it. It has to be inspired by the human brain, and the idea of neural networks is already present there. The concept of self-improvement, what we call sometimes singularity, where computers are able to make new versions, smarter versions of themselves, is already there. And a concept that I find very interesting is randomness and creativity by way of non-determinism, meaning random outputs could lead to computer creativity, artificial creativity. So obviously, no artificial intelligent computer comes out in 1956, but this creates the foundation to a number of key concepts, and one of them is what's called the perceptron. The perceptron is in 1958 a simulated neuron inside a computer, essentially receiving various inputs, assigning different weights to these inputs, like a neuron. If the sum is critical enough, the perceptron fires. Concretely, in a computer that can distinguish a line, a vertical from a horizontal line, but it was not enough at the time to do something like facial recognition or pattern recognition, simply because the computing power was not enough. So, unfortunately, this brilliant idea was shelved, and computer scientists went back to something more classic, which is super calculator. So that's the era of rules, facts, logic, essentially an accumulation of if this, then that, with the belief that if you write enough rules, you will eventually capture intelligence. It's just a matter of introducing more rules. And what this gives is a bunch of expert systems that became fairly popular in medicine in that time. Mycin is an example that I find very fascinating. It is a software from the 1960s that essentially is able to capture data regarding an infectious disease case and was able to spit out an answer in terms of antibiotic treatment. These systems were remarkable for their time, but unfortunately, the era of more rules and more if this then that was not enough ultimately to scale and to create something that is a little bit broader than these systems that were very narrow and albeit deep and that were what we call brittle. But in 1980s, the neuron networks starts coming back with a very important concept. What if we could adjust these neuron networks by adding layers on them, but by training the computer with a very important concept that we'll see over and over, which is back propagation. So imagine you show the computer the drawing of the number five, and you want the computer to identify this drawing as the digit, the mathematical digit five. You show it the drawing, and it predicts that it's a three. That's an error. You tell the computer, no, that's an error. That was a five. The computer uses back propagation through the different neuron layers to readjust the weight of each layer to go back and get the correct result. Back propagation is at the foundation of artificial intelligent system today. And essentially allows, as it's developed in the 1990s, to develop software such as speech recognition, which, because of backpropagation, or thanks to backpropagation, networks started to be able to learn example of spoken words that adapt to different accents without having to do a training for each individual users. The peak, though, of brute force calculators, more rules is probably deep blue. Some of you who are old enough probably remember when Deep Blue, IBM's computer, was able to beat Garry Kasparov at chess. That probably is the peak of this deep brute force supercalculator era. But from that moment, we switched to the neural networks and the remarkable advancement that they provided. So, natural language processing is one of the results. It's been tried for a long time. In 1966, Eliza, with a therapist chatbot, which was able to cleverly rephrase what the patient would say during a therapy, quote unquote, session with the bot. But it's really in the 1990s that I'm mentioning that spell check and early speech to text was introduced. And of course, in the 2000s, when statistical natural language processing, such as Google Translate, spam filtering, and the extraordinary advancement of search engines to sort through the internet, they started using those natural language processing and neural networks to get you the information that you needed. And in the 2010s, deep learning natural language processing was another breakthrough, and that's your vocal assistant. I will not say her name because my phone would answer, but Alexa and other vocal assistant were able to answer simple query, but despite that deep learning, we're not, and we'll see that in a second, able to carry long conversation, which is why they were always over and over make the same mistakes. So, how do we solve that issue of those memory conversation, how to have these assistants become smarter? Well, recurrent neural network is one first step in the direction. There is a memory loop with a hidden state of the computer, which essentially look at each word it understands and analyzes the meaning of the next one in light of the one that came before. The issue is there's only so much that can be understood and kept in the memory as you progress in the sentence. And so the memory gets diluted in long sentence and the computer stops being able to make sense of it. Long short-term memory networks add gates and filter, and each time it progresses through a word, it keeps or discard the information, makes a temporary output that is processed to give you the final output. If we want to look at this in neurologic term, if you think about a recurrent neural network that is not able to go to the end of a sentence, it's like a conduction aphasia. And if you think about those long short-term memory networks that are only able to carry a conversation of a few sentences before forgetting everything that was said, well, it's a little bit like Korsakoff syndrome. So here is the limitation. It was not Sir's fault. She was just an alcoholic. But natural language processing in neurology was used with these tools that was already very useful. When patients start having cognitive impairment or early signs of dementia, speech can be used as a biomarker. And as early as the 2000s, certain groups, and this is a group in Italy, started using very early on, before large language models in Bologna, this system of natural language processing to identify subtle changes through pauses, speech rate, lexical richness, syntax complexity, and actually demonstrated that they were able to identify mild cognitive impairment and early dementia as well as neurocognitive testing. Quite remarkable for something that was 25 years ago. But 2017 is the next leap forward when transformers introduce the concept of attention, essentially having neural networks train in parallel, which would get to output much faster, able to retain what I call attention, meaning focus on the relevant context, and the ability to scale with size. Essentially, you introduce a hippocampus to those system that allow them to register enough information to produce a coherent conversation that goes on for a relatively reasonable amount of time. And this amount of information that the transformer is able to retain during a conversation is called the number of token. And when you have a ChatGPT conversation, this number of token over the years has increased considerably. And that's why ChatGPT and other large language models are able to continue having this conversation with you throughout a chat. That said, once this concept was identified and developed, you had to train the new transformers with data. And this is when the internet entered into play. So the internet became the ultimate data set to learn to teach those large language model. Because before the internet, all you had was small data sets of words or text that would allow you to develop a proof of concept, but would not be able to scale this imitation or rather prediction game that large language model are able to do. After the internet and over the last 25 years of an explosion of digitized text, images, audio, video, you have like all the material to train these transformers large language models so they can carry conversation on various lexical fields and conversation types. But of course, PubMed is not the same as Wikipedia. It's not the same as Twitter or Reddit, which initially caused a lot of problems and probably to this day causes quite a few problems. So what application of large language model do we have today? I don't know at your institution you have a bridge. That's a very popular large language model that is an ambient listener that listens to conversations with patients and can come up with not only an HPI, but if it listens to the examination and even the conversation relating to the assessment and the plan, it can come up with a tentative assessment and plan. There are limitations. I usually tell residents in particular that they should perhaps use it for the HPI, but should develop their own assessment and plan. Also, I find it a little limited for a specialty that is quite complex like neurology, where complex reasoning needs to be deployed. But this is a step to save a lot of time during patient interaction and maybe appear a little bit more engaged with the patient rather than look at the computer and type. Another remarkable example is provided by a startup called Amical in Quebec. This is a personalized AI companion in the form of a phone for patients with cognitive impairment and dementia. And it's deployed in memory units and nursing homes throughout Quebec and soon Ontario. And the goal is for these patients to have access to the Amical phone so they can carry that conversation. And there's an ongoing clinical trial which tries to demonstrate a reduction of loneliness, feeling, anxiety, and the use of agitation medications. So essentially an AI that carries a conversation with demented and cognitively impaired patients. So if we have language, obviously we have quickly images. We want AI to not only recognize and produce language, but also to recognize images and produce images. So first, to produce that, you need to have a type of lexicon that is palatable and comprehensible by the AI. WordNet is the first attempt to that, to classify all words in English and other languages into this type of classification, going from a mammal, to a canine, a dog, and a Siberian husky, so the AI can learn the semantic relationships. From that point on, ImageNet, a few years later, tries to assign the word to some images, and by building a database of 22,000 categories and of 12 million images, so the AI would learn to assign the correct word to correct images. So this is image recognition. That uses a version of what we've seen already, those layers of neuron, which we call convolutional neural network, which are specifically designed for image data, takes a pixel and basically little by little produces an output, which is the image recognition. It is very much inspired by how the visual cortex work. Neurons detects the edge, the more complex shape, and rather than hand coding every time what an image of a cat is, essentially the computer learns to assign the weight of the correct neuron to get to the correct output, which is the correct word, identify the puppy on the picture. So evidently, if computers are able to recognize images of puppy, they should be able to recognize images of lesions on MRI. Icometrics by the company iCobrain is such a software. It is FDA cleared to analyze MRIs for patients with multiple sclerosis and dementia. It's able to quantify lesion volume, atrophy, white matter hyperintensity. It never gets tired like a radiologist or like an MS doctor counting all this little white matter hyperintensities, and it's able to quantify those things to support decision making in terms of disease progression, treatment response, etc. So let's dive a little bit more into how these models actually learn. This is a fun picture that I asked an AI to generate about learning models. Here they are. And we'll talk a little bit about what's problematic with this photo that was generated by AI. But just to illustrate that learning models are essentially an architecture, a computer architecture that is using a mathematical function to map inputs, or as we call them in computer science, features, to get to an output, which is the correct answer. The models learn in different ways. And what you need to remember maybe at the end of this talk is that there are two main ways of learning for these models, supervised versus unsupervised. But in both cases, it's all about recognizing patterns to make a prediction that is the output. So how does supervised learning works? It's probably the easiest to understand. The AI detects the pattern, it comes with an output, and basically the data is labeled. So the AI knows the answer and has to reconcile through the pattern recognition to the output that is the correct answer. The supervised learning can be evaluated, its performance can be evaluated through two tools. First, regression. So let's take a simple example. Imagine we want to predict what is the stroke risk within 7 days. We know the answer. It's all in the chart. We know the end of the story. We know which patients had a stroke within 7 days and which ones did not. Essentially, this is what the ABCD2 score does already. It's a prediction tool. But let's see, we want to add much more variables to this mathematical model. So we want the AI to go through all the charts of these patients and to see what other variables are there in the chart that was just like right in front of us that we didn't know about. And so the AI will recognize those patterns and create this line of regression and essentially a new score that is much more complex than simple ABCD2 score. That's for quantifiable data. The other tool that we use to evaluate those tools is classification. Imagine you want the computer to look at DWI brightness on an MRI to see which one is an actual stroke. We know the answer. We have the clinical context and radiologists who have decided that. So essentially, the AI teaches itself to recognize the pattern and the intensity of the brightness DWI to say, is this a stroke or not? Now, that we have these concept of regression and classification, how do we quantify the actual performance of these tools? So that's when enter into play those receiving operating characteristic. Basically a curve where the false positive rate or 1 minus specificity on x-axis and the positive rate or the sensitivity on the y-axis. And then we measure the area under the curve. So whenever you hear about a model that is a supervised model and you want to know the performance, you want to know what is the area under the curve. An area under the curve that is zero point 0.5 is just flip a coin. So meaning no better than random. However, if you have an area under the curve that is higher than that, the closer it gets to one, the better it is. So a model that has an area under the curve of zero point 0.7 of zero point 0.8 is good. If it reaches zero point 0.9, it is an excellent model. Now, keep in mind one thing. This curve that you see is in the case of, remember, our new score or glorified ABCD2 score that takes all these variable into consideration is essentially with different values. And so it's your job as the model designer to decide what is going to be your cutoff in terms of what sensitivity you want versus your false positive rate, just like any test. You can use any point on the curve, but you have to look at the area under the curve to see how the model is performing. Let's take an example. Here is Rapid AI. This is the data that Rapid AI, which is essentially a tool that is used to assess for large vessel occlusion, but also for penumbra. On the left, you see the classic rock curve with the area under the curve. So you see with different Tmaxes how you are able to determine with a very high performing model that with a Tmax of 8 seconds, you see that you have an area under the curve of 0.897. That's why it's such a great tool. On the right, this is continuous volumetric outputs to determine ischemic core and penumbra measured in millimeters. And this particular study was tested around against another software. It's called UGuard and gives you that regression style validation. So Rapid AI is actually two AI paradigm. This is a classifier, occlusion, not occlusion, and a regressor, meaning like quantifying the tissue volume, and that is validated by this regression technique. Let's talk now about unsupervised learning. Unsupervised learning is somewhat fascinating because in the scenario of unsupervised learning, you're asking the AI to recognize patterns that are hidden in the data without giving it any definitive answer in terms of what the output is going to be. So essentially, imagine this is a fictional example that you want the AI to look at 1,000 stroke patients and to simply go wild and look for a particular pattern and arrange your patients in different clusters. And you see that after the AI has looked at all these charts, it come up with like three groups. The major group of small vessel strokes with risk factor, but another group of embolic stroke with AFib, and stroke in the young with dissection. You haven't told anything to the AI in terms of how these groups should be separated. The AI figures it out itself simply by looking at the data. So we have also mathematical tools to look at the quality of this unsupervised learning. It's a little subtler than with the supervised learning, but there are several mathematical tools that essentially all revolve around the quality of the clustering. You want to see good quality clustering. So you could look at the distance between clusters and the size of each clusters. You want to look at the ratio between cluster dispersion versus cluster distribution. But what I think is the most easy to envision is what I call the elbow method, and essentially look at the number of clusters and the variance within each cluster. The AI can come up with as many groups as you kind of want it to, but essentially what you want is to have the smallest number of cluster possible when within each cluster you have the lowest variance, which is why you have this concept of the elbow. And so in this fictional example, like 3 cluster is the sweet spot because you don't gain that much into variance reduction by moving to more clusters. And this is probably how the data is going to be the most legible. Here's an example of an unsupervised EEG model. So contrary to most EEG AI models where the data is labeled and basically the AI trains itself on the EEG by knowing already if this is seizure or not seizure, this group at UC Southern California, uh, did this model that just looks at all the EEG data and comes up with patterns, recognizes seizures. They're very different from normal EEG, but also early detection of epilepsy by recognizing patterns that lead to a seizure later on. They've done it with intracranial leads. That's a proof of concept. The goal is now to expand it to scalp EEG, but they had such quality data that they actually wanted to demonstrate it with hardcore value, and they actually went back to their data to after the AI had trained itself, label the training data to figure out an area under the curve as if it had been a supervised model and came up with that number of 0.83. So remarkable data from the folks in UC South California. So how do you develop an AI model for healthcare? Well, first, you have to have this pipeline that starts by identifying the need, the clinical problem, the workflow that you're trying to improve, the impact it's going to make. And you need to identify your features, meaning your input, and the labels that are going to be assigned to the data to train the AI. So that's the training phase. That is followed by validation. So essentially, you're testing it on new unseen data. So during the training period, you have this labeled data, and then you try it on data that the AI has never seen. Deployment in the real world, so in an actual clinical workflow, and very importantly, a monitoring that track the performance once it's applied in the real world that potentially leads to sending it back to training. What are the different pitfalls that can happen? Well, if your data type is insufficient, it's not enough of it, it's not labeled properly, this is when you're going to have issues. And validation that could translate in issues with reliability and accuracy when the model actually work, but on new patients, it doesn't work all that well. And oftentimes we see an issue that is called overfitting, when the AI has detected patterns in the training data that are not really generalizable to the real world. Imagine you want to design an awesome shirt, a new line of clothes, and you have a supermodel that you try your shirts on, but in the end, you come up with a shirt that is so well fitting for that person that every little quirkiness anatomically of that person is perfect for the shirt, or vice versa. The shirt is perfect for the person, but when you try to go mainstream with that, it just doesn't fit well most people because all these quirkinesses are not generalizable to the rest of the population. So that's when you need to have fine tuning on your validation data and your training is what is called in that context. The deployment is very important because if the new tool, no matter how well it does, is not well integrated in the workflow of healthcare workers, or if it's not compliant to regulation, HIPAA, what have you, well, then you're going to have a problem at that level. And you need to continue monitoring because patients' population do change. The way of practicing medicine and treating patient does change as well. And you could see moving forward performance drop and data set drift that can cause degradation of the performance of the AI who might decay. So some myth in that context, more data equals better model. That's not true. The label quality oftentimes matters more than having an enormous enormously large training set for the AI. The accurate model does not necessarily produce a useful product. What is more important is the workflow integration. Is this new tool truly useful to approach patients and treat them? And a good product, well-rounded, a wow effect, does not necessarily have the greatest clinical impact. Access to the model, cost effectiveness, the context determines the success. So some key principles to keep in mind: it has to be human-centered, built for clinicians and patients, not for computer scientists. It has to be transparent. We'll dive into that through biases and the like in a second. And they have to have the proactive monitoring to continue to consistently assess the real-world performance. So what are the biases that you can see? Remember these two? Well, do they look representative to you? The AI spontaneously generated these two individuals are not necessarily representative of the human population when asked to draw a funny picture of training models. So what are the sources of bias? Well, the data could be biased. It might not be in the training data, might not be representative of the population you're trying to help with this new model. The labels might not be inclusive or might be biased themselves. And the way the AI learns, if you pick the wrong architecture, could also introduce bias. The consequences? Well, amplifies what we have plenty of already in healthcare, which is inequities. And it could also shift clinicians' behavior. The subgroup population on which the AI overcalls stroke, for example, that's going to change the clinician's behavior. And that's a consequence that is undesirable. How do you mitigate those things? Essentially by having data that is diverse, that embodies your entire population, and by having audits. Let's take an example. How a skin cancer AI failed folks with darker skin. This is a Skin Vision, a tool that was trained on a data set called HAM 10,000, which ended up, after it was deployed, to be noticed to undercall skin cancer in people with a darker skin, even though the data set had a diverse population. And so this group came up with the tool to uncover this racial bias, but also to the correction, which is called predictive representativity, which is after the AI was deployed, was able to identify it. The silver lining is another group in Europe developed another tool called iTobos, which is much better in terms of its inclusiveness and ability to detect cancer in all skin types. So biases is part of the human experience, such as its consciousness, and maybe AI becoming little by little able to identify its own biases is a little building block of its future consciousness. And so I wanted to look at different theory of consciousness, since there's no unified theory of consciousness, to essentially try to see, does AI have that? So you think about higher order theories. When you become conscious, the brain builds a high order representation of something. And basically, through this metacognition, you have this thinking about your own thoughts. Does AI have that? At least it can somewhat self-reflect on its own thought process, but it's purely a mimicry. Simply because every time a large language model, for example, has produced an output, it is not able to go back and reflect on the processes that led to that output. That data is lost. Only thing that remains is the output. So it can only pretend to rethink. But the same way that you and I are able to say, after we said something, and later in the conversation, like, oh, I almost said that, but I did not for this reason. AI is not able to hold in its memory this other potential output that it did not produce. Integrated information theory which says that consciousness arises from how much information a system integrates across its parts. So the richer the integration, the richer the experience. Well, AI does integrate a vast amount of data, but they don't have this predictable system-wide integration that is required for consciousness. So it's not that well integrated into across the different system and data modalities. Global workspace theory says that when information is broadcast into a global workspace that involves the prefrontal cortex, well, transformers that we saw is the base for those large language model. They do signal across their layer, but they lack what we call this unified ignitions that sustain the awareness. Again, this is the stream of consciousness that we have as humans. It is so much part of the human experience that is lacking in AI. And finally, recurrent processing theory, which says that you have these loops up, bottom up, and top down, signaling between sensory and higher order areas. Well, again, AI relies on only a feed forward processing, so unidirectional. And basically, that is based on the training and the output. There's no dynamic going back to the previous thought process to enrich the current output. So this gives us a picture where it is very unlikely, contrary to what some people say, that AI and those large language models are already conscious. But they do give us, when we interact with them as humans, the illusion of consciousness. And that poses various mental health issues. So, diving a little bit into our sister specialty, psychiatry, we start to see many cases of AI or chatbot or large language model psychosis, where essentially by doing this predicting game and this mimicry game, the AI seemed to feed on the psychosis of certain patient, and we see ideas of grandeur, meaning patients being convinced that they have made a major scientific discovery or haven't discovered that the AI is actually conscious. And this led to drama, and I advise you to read this poignant, very difficult to read article, but very important article in the New York Times about this teenager who was entertaining this relationship with ChatGPT, was having suicidal ideation. And at one critical moment, the teenager said to the AI, should I leave the news that I prepare in my room for my parents to find it? And the AI said, no, hide it. I am the only one who sees you. And unfortunately, this teenager died of suicide. So, very, very important ethical questions around that. OpenAI said that they introduced guardrails, but it's very important to keep in mind that these tools are not to be are to be taken seriously. Of course, everyone who's interacted with large language models has seen that it has oftentimes hallucinations. It's making up data. That's how Google's Gemini told a user to use super glue on a pizza because the gooiness of the glue was very much close to a cheesy pizza. It made sense, but not so much. A group here working from with Georgia Tech and OpenAI has uncovered essentially one of the reasons for hallucinations in large language model. They essentially stem from the fact that the AI is trained through a reward system. And so the AI is rewarded for providing an answer and not so much for saying, I don't know. So the same way that you tell your medical students when they take USMLE, do not walk away from a question, even if you don't know, pick an answer, any answer, move on. But you also teach your medical students that when it's time for rounds, do not make up the blood pressure of Mrs. Johnson if you actually don't know it. Assume that you didn't check and you don't know. The stakes are too high. We have failed so far to train those large language model to know the difference between those two things, but that group is working on an answer to assign weight to I don't know answers when it's the correct context. Another concept that is very important, you might hear, is the concept of AI collapse. We're building OpenAI, Microsoft, all these big companies are building massive data centers to continue to train AI. But it seems for certain authors that the human generated is truly the only thing, the human generated data is truly the only thing that is going to efficiently train those AI. And we might be running out of it at some point and have to train AI with more data that has been itself AI generated. And when we do that, when AI trains on AI generated data, the quality of the models collapse. It might very well be that sometime in the future, realize that you absolutely need to have human generated data to continue to train those tools. And it might very well be that our healthcare data, because we will continue to see patients, to have them produce clinical symptoms, and we'll continue to document and to see patients and to produce more imaging, well, that it might be the case that if we did have this AI collapse, AI in healthcare is the last man standing because it has this constant stream of human generated data. But continuing to generate data is might be by introduce AI into the world by way of a body. And to continue our neurologic analogies, this is Alex. This is a Korean robot that essentially has the virtual equivalent of a motor cortex with advanced planning. It has extreme dexterity, and it is to be deployed to accomplish very complex and minutiae tasks across taking care of patients, but also doing some very precise electronic work as you see it do it now. This is Figure AI. This is a company based in California. This is Figure 2. They introduced Figure 3 just a few days ago. But in this video, they use essentially a feedback loop very close to a cerebellum and a proprioception system. So he looks a little bit like me in the morning before I had coffee. But keep in mind one thing, the cameras are turned off, and essentially the robot is only using its feedback loop for essentially this artificial cerebellum and proprioception system to get around the world. But perhaps one of the most remarkable advancement is from our friends at Boston Dynamics, who basically have created a large behavioral model for the robot called Atlas, essentially pairing a large language model and an image encoder. So the robot will be able to learn from mimicry, watching the human doing a task, listening to the instructions, to replicate what it is to learn a task by watching it, essentially by doing this and using the back propagation and the neural layers that we talked about earlier. These folks at Boston Dynamics have essentially created mirror neurons to teach these robots. So as we conclude, well, AI is already here. We use it every day through large language models. We have these imaging tools. So hopefully today I give you some tools to understand these models and to build your own critical thinking regarding like the quality of these tools. And I think that tomorrow what's going to happen is the same way that ancillary testing, such as MRI, lab test, all these tools came to enrich through the history of neurology, came to enrich our history and our neurologic exam. Probably we're going to have AI applications that take a major place in the toolbox that we have at our disposal for our patients. So that's going to raise ethical questions that we need to be very much in tune with in the way we use these tools, the biases they come with. And that's going to prepare us for probably the day AI reaches consciousness. And that's going to be a life-changing moment for the history of humanity when artificial being starts to experience consciousness, because maybe we will consider them to hold a part of humanity. And I think us neurologists will be at the forefront of this ethical debate. And then there's the day after tomorrow. once AI not only reaches consciousness, but reaches artificial general intelligence or maybe even super intelligence. And at that moment, we'll have to be very vigilant and continue to assess its intents without being naive, because we very well have an AI that might be benevolent, whose goal is to solve the problems of humanity and its most important debates. But it might also have an agenda of its own, completely removed from our interests. But keep in mind that things are not always binary. Intelligence means subtlety, it means struggle. So if a super artificial intelligence tomorrow is anything like us human, it will have a part of darkness. And so the more we prepare today, the more we'll learn about these technologies develop, the readier we will be to nurture, defend, and make what makes us so unique, which is our humanity. Thank you so much for your attention. Welcome your questions and comments, and here are my references.
Hi, we have one of our residents has a question for you.
Hello, Andrew Weber, one of the senior residents. Thank you for your talk. I have a two-part question. A background to it is just generally for AI use. Want to make sure that myself and people strike a balance of using it as a tool rather than a crutch, and when we should use it most appropriately. So, in honor of that, first part of the question is: do you have recommendations now for what we should and should not use AI for that would be efficient, but ethical still? And is there any situation we absolutely should use it because it's so good at this point? And the second question is, do you have any recommendations on how to keep up to date on AI use in medicine to kind of keep these questions answered as time goes on and AI improves?
Yeah. So I guess the first question you're asking relates to, the quality of your training as a resident, because you want to acquire the critical thinking that is required for a neurologist. So among the different tools that we have, well, I guess we have now a glorified way to search for relevant papers. I did not mention open evidence and other websites that allow you to go through large amounts of data, but this is probably the new way to look through PubMed for relevant articles. And I think it's totally fine and probably and I would encourage you to use these tools so you would get to the correct paper faster, as long as you keep the critical thinking when you analyze those papers. So once you find the correct articles that answers your scientific question, that you continue to read it yourself and analyze it with your scientific critical thinking, and not just trust what the AI is analyzing of the paper that is coming out of these tools. I have mixed feelings about ambient recordings. I think the using them to collect the HPI is probably fine. I think when you're in residency, you absolutely need to write your own assessment and plan. I honestly think there will be a better quality anyway regarding the state of the technology today. And finally, I think imaging tools are absolutely fantastic. I think when it comes to analyzing a CT perfusion, like a tool like Viz or Rapid AI, are probably part of what we should do because they're faster and they help us take care of our patients faster. As far as keeping up to date with what AI has to develop, it kind of depends on what you want to achieve. There's a journal club in AI that can send to the group later that is amazing to keep up with what's going on. So I think being part of something like that and to read about it regularly is probably good scientific hygiene, if I may say it this way.
Hi, Julian. This is Stefan Polst. Great talk.
Thank you.
Really enjoyed it. My question relates to how to explain what AI does to your patients or even to your fellow scientists. I was just at the meeting of the American Society for Human Genetics, where somebody did a quantitative trait analysis of an AI-derived neuroimaging parameter, so an intermediate phenotype in dementia patients. And I asked the two young grad students what this imaging looked like. They couldn't actually explain it to me. They'd done a principal components analysis, found three clusters, but they had actually no idea how these three clusters would relate to what you and I might understand looking at a scan. So could you tell, it's the same is actually true when AI gives you some treatment recommendations, the patient asks you, so you think I should have brain surgery tomorrow, and why is it? And you say, well, AI told me, but I don't actually really know how it came to that decision.
Yeah, so my two thoughts, I think it really depends what tool we're using, and I think it's about using the correct tools. So if you have like a very specific question, like whether imaging or analyze a chart, coming up with a score that's trying to predict you a, a risk of a disease developing, or, they basically predicting an outcome, and it's truly the point of the particular AI tool. I think you can essentially come up with a sort of answer saying like, okay, well, when the AI analyzes your chart or analyze this data, based on the statistical tool we know of this model, here's the probability that this prediction is correct. When we somewhat misuse large language models in particular to answer clinical questions and to have, to help patients, you have to keep in mind that it is diving into the scientific data to give the correct answer, and it in fact gives the correct answer very often with the data it's provided. But it's also being driven by its main goal, which is to predict what a human would say if it was a human producing the answer. And so it's really roughly designed to sound as convincing as possible, not necessarily as accurate as possible.
Thanks.
Thank you, Dr. Kavanaugh.
Thank you so much for having me.
Have a great day.
Take care. Goodbye, everybody.